will enhance survival. And we think that probably is also operating in humans. There's some evidence from way back from Andrew McMichael, way back in 1983, that recent exposure to another flu virus will give you some protection, and that this probably went through CD8 T-cell immunity. Then all the viral immunologists all dropped flu, including McMichael, and the reason for that was HIV. So for a long time, there was very little done on each human flu immunity. That's come back much more recently as we've become much more concerned about it. And we have people like Suzanne Epstein and various people who are now correlating the degree of T-cell immunity with the degree of protection and finding some protective effect, and think there's a real role for CD8 T-cell immunity in a vaccine type preparation. There's a lot of movement on that front. You'll have read recently that everyone solved influenza by making vaccines. Arno Moorbacher in Canberra solved it. Adrian Hill in Cambridge has solved it. Ab Osterhaus in the Netherlands has solved it. We've all got vaccines that are wonderful and are going to stop flu, and let's see what happens. This is, I'm going to draw this to an end fairly quickly. This is some work from Canberra, from Melbourne basically, from Catherine Kizerska, and showing that an actual fact, with the nuclear protein peptides that are recognised by humans in this H1N1 swine virus, they are actually pretty much the same as the ones that were in the 1918 flu. Here you can see the differences between recently circulating H1N1 strains and the swine flu one, the seasonal ones that were circulating before. And here you can see there's really pretty minimal difference from the 1918 one. And so it's been very conserved in the pigs over the years. And of course that particular peptide won't have been under selection in the pigs, because this is one that's presented by human MHC molecules, not pig ones. We've also looked a bit at, this is Christine Orzansky's work in Memphis. We've been looking at kids coming into the children's hospital, the Bonner Children's Hospital, and you can see that here's a pulse of H1N1 infection going through children. And they managed to get a lot of good samples from them. The T lymphocyte response in kids looks very much like the T lymphocyte response in mice. CD8 T cells predominating in the lung. They're now starting to work that through, and they're having occasional cases of H1N1. We've looked at cytokine levels in some detail. I'm not sure I'm pointing us the right direction or something. And these are the ones we found that are particularly prominent. Interleukin 8 seems particularly prominent. Interleukin 6, and chemokines as well. Also, there's a reasonable amount of interleukin 18 made, which is pretty much associated with the inflammasome response and is associating with the healing or severity of inflammation. So that's also intriguing. The other thing we're doing is the systems biology thing that I mentioned. And as I said, this is really fascinating. It has us working with a lot of computer guys and software guys. Systems biology at the moment is really functioning at the edge of the actual mathematical computing software edge for really handling this data. The same is true for the epigenetic work that Steve Turner and his colleagues are doing in Melbourne, trying to understand regulation and what it is about, say, a memory T cell or an effector T cell, which is different in the long term in view of its epigenetic marks and the changes in genome. So a lot of this stuff is really operating right at the edge of the science. And it's pretty fascinating, and we get wonderful diagrams, which these sort of diagrams in the past, immunologists used to draw them, linking various things up, and they made it up out of their head and drove everyone completely mad, and which is why a lot of people were really annoyed with immunologists. But this is actually drawn by the computer, and it shows us up pathways that we really should be looking at in much more detail. So what's happening in a lot of this infectious disease research is that these new approaches are suggesting to us potential targets and potential systems that really need to be looked at in great depth. And we need to understand these things. So science at this stage is, because of the new technology, is really in an expansion phase. There are enormous numbers of things to do. The only limitations really are how much resources we can get to do those things, and of course how many decent jobs we can get for young people to go ahead and make those analyses. So we keep trying to talk up science and say just how great it is and how we need that. With flu, maybe a belt and braces vaccine that does focus on this cross-reactive antibody type strategy and also focuses on T-cell responses might be good. Maybe if it was even if it was only partially protective and we just got a little bit sick but we didn't get very sick, it would be a real plus. This business of having to make a new flu vaccine every year is really very difficult. And for instance, with the swine flu vaccine virus, which got from Mexico to Australia within a matter of a month or two, and then went right round the world very quickly, we had a 6-month lag before the vaccine was available. Now, that's okay if you've got a virus like that is not highly lethal. But if that virus had been killing at a high rate, we would have been in trouble. We had the antivirals, but there's a lot of Tamiflu resistant developed very quickly, especially with the N1. And how much antiviral can you put out there? And then the question is, you know, you're waiting. What are you using? Well, with influenza, you would try to isolate people. Modern face masks may work a lot better than they did in 1918, but you've really got a problem. So if we could actually make some sort of cross-reactive vaccine, which would recognize a lot of different influenza viruses, even if it wasn't optimal, but it decreased the severity of disease, and we could stockpile a vaccine like that and keep it, or use it for that matter, then we might do a lot better if we do get a very severe influenza outbreak, which is, of course, what worries everyone. It doesn't just worry the scientists and the public health people. It also worries the business people and the politicians. And the reason it worries them is because we know that the SARS outbreak, which in the end was relatively localized, only killed about 800 people, caused something like $50 billion in economic damage. It's because of the shutdown of hotels, the shutdown of tourism, shutdown of the airlines. You get enormous economic damage. It took Singapore several years to recover. It took Toronto longer than that. That was the only North American city that was really hit. And so everyone is acutely aware now of just how dangerous and how economically damaging a global influenza pandemic can be. Of course, it can't be as damaging as criminal New York financiers who caused the global financial crisis. And they haven't even been shot, so I don't understand that. We should send them to Libya, maybe. Okay, so on that very, I shouldn't have said that. I withdraw that remark. I just wish someone would plug Gaddafi. Anyway, there we are. So, bird flu. Bird flu we haven't been worrying about as much, but it still could be highly lethal and dangerous. We're a lot more worried about the pigs. So thanks very much.